Welcome back to the Simpkins Physics Corner. Today, rotational kinematics for AP Physics. Let's jump right into it here. The London Eye of Ferris wheel on the banks of the Thames has a radius. Oh, sorry, that's the second one I wanted to do. My bad. Good start to the video. Potter's wheel. This, by the way, is on your 5.1 packet. The last two problems we did last time we were together. Potter's wheel rotates from rest to 210 revs per minute in a time of 0.75 seconds. So let's go ahead and drop some stuff on here already. We're talking about revolutions per minute. I'd prefer radians per second, which we'll get to in a little bit. But I'll just go ahead and write this as revs per second, and I'll explain why here in a minute. And then the omega final, the final rotational speed, is 210 revs per minute. Now, we like seconds because we see seconds a lot as our standard unit in physics. So I'm just going to go ahead and clean that up real quick with a quick conversion. So 210 revs per minute, if I multiply that by 1 minute over 60 seconds to convert, I'm going to get 3.5 revs per second. So that's going to come in handy here as we move forward through the problem. It says it does that in a time of 0.75 seconds, and then it asks us a bunch of questions. So the trick with this unit is there are a lot of terms that we need to know the difference between these things. Like there's 4 kinds of acceleration when you're talking about moving a bike wheel rolling down the road. So this first kind here, angular acceleration of the wheel, what is it? This is the first question. So angular acceleration is the alpha, and that's going to be defined as the change in omega, rotational speed, over time. So alpha equals delta omega over t. You can also see a version of that equation on your AP Physics equation sheet. So delta anything is that quantity final minus that quantity initial over t in this case. And so we're going to go ahead and plug this in for the change in omega over time. Now you see why I chose to do 3.5 revs per second here, because when I do alpha, I'm going to do 3.5 revs per second minus 0 revs per second over 0.75 seconds, and that's going to be equal to, I guess I'll have to drop in my calculator, won't I? Actually, I already did. That is going to be equal to 4.67 revs per second squared. Okay, so that is our current alpha. Now, if this bothers you, if this unit bothers you, it bothers me a little bit. Our standard unit for alpha, in fact, we'll need this later anyway, is radians per second. So I'm going to table this one. I'm going to keep that because it's going to be useful for us, but I'm also going to convert it into radians per second. So 4.67 revs per second squared. I'm going to multiply that with the revs up top there. I'm going to do 1 rev on the bottom and 2 pi radians on the top. That's how you would convert from revs to radians there to cancel that out. And I'm just going to kind of keep that in my pocket here as 29.3 radians per second squared. Turns out we're going to need that later anyway. So that's part A. I got 2 answers, but they're the same. They're just in different units. Okay, we'll keep going. All right. Come back here. Cool. Sorry about that. I had to fix a little lag there. So how many, we got the angular acceleration, assuming it's constant. Part A is done. How about part B? How many revolutions does the wheel make during the time interval? Now, this is another thing. You're going to see this term, how many degrees did you sweep through, or how many revolutions did you make? This is actually, we got to know what they're asking us for. This is actually asking us to solve for this delta theta. Remember, when we do circular motion, theta is defined as the angle that you sweep through the circle, and that is called angular displacement, and we call that with the variable, or we identify that with the variable theta. All right, so we look on our equation sheet again, and we see an equation that looks very similar, just with all different variables. All right, so we can look at it like this if you want. Omega t plus 1/2 alpha t squared is going to be what that equation looks like kinematically. Oh my goodness, these slides. Hold on a second. All right, one more shot at this thing. Okay, so here we have our equation, and so we can plug this in. Now, the omega initial is 0, so that's convenient because all that goes away. And so really all we have to do here is plug in 1/2 alpha, which, if we're going to use this equation for delta theta, it does say how many revolutions does the wheel make. And so now you see why I did keep this one here, the revolutions per second squared, this guy over here, because now I can just plug it in those units. The units matter here a lot. So 4.67 revolutions per second squared times our time, which was 0.75 seconds squared, equals, and we can plug that in and get our answer for delta theta of 1.31 revolutions. All right, so that is when it says how many revolutions did it do. That's our solution for that. All right, so I'm going to swing myself up here since we've already done part A. The last part here says find the tangential and radial components of acceleration. So different textbooks do weird things, and this is one of the weird things that it does. Is tangential, I'm cool with that, right? We already learned this equation last time. We said that if you want to go from rotational stuff to translational stuff, you just whoosh, slap an R on it, right? And so we do alpha times radius there to get the tangential acceleration. But I had to look this up. I just Googled it. P.S. You're allowed to use Google. This says, what's the radial component of acceleration? Turns out that what they're actually talking about is centripetal acceleration, right? It's just a weird way to say centripetal acceleration is radial acceleration. Who even uses that, right? But they do, so that's what we have to use. And so those two equations were both from our notes last time. And if you got hung up on this problem, it's probably just because you had no idea what radial component of acceleration meant. Now, we are arriving here now with our radius here. So we have our radius of 0.12 meters, but we're arriving at a different place in the problem. You see, originally it said 0.75 seconds is how long it took, but that's how long it took to get to 210 revs per minute. In this case, we're only going to 180 revs per minute. Now, it may concern you, but the one thing that we can count on is it does say assuming constant angular acceleration. So while 0.75 seconds is now off the table because that corresponds to 210 revs per minute, we can assume that we still have the same acceleration happening here. If you went and did the math, you would find that you get the same answer there. So let's go ahead and look at then what are these components? What are these components going to be? Well, for the tangential piece, I'm going to move it down here. Sorry, I'm practicing terrible whiteboard etiquette. The tangential piece of our acceleration is going to be alpha. Now, keep in mind, this is why I did this earlier. You see? The equation, if I'm going to take this, I'm going to be multiplying radians per second squared times meters. And remember, when the meter shows up, it's like, huh, I'm a meter. And the radians are like, ah, and they run away. So what you need to do here is make sure you use the one that has radians going on there. 29.3 radians per second squared is going to be our alpha. And our R, our radius, is going to be 0.12 meters. All right, and so, sorry, this is getting super streaky all over the place here. But if we plug those guys in together, that's looking like a little bit of 3.516, and we're looking at tangential, so it's meters per second squared. And you notice meters here cancels with the radians here. Why? Because when the meter shows up, the radians are like, ah, and they run away. And so this is your answer for your tangential component, or in this case, the tangential component of acceleration. Now, as far as the radial component, well, what they really mean is AC, or the centripetal acceleration, which is omega squared r. And so for that one, you can go ahead and plug in your values. In this case, the omega is the speed that we're currently going at, that's where this 180 comes in, right? And so just a real quick little conversion, 180 revs per minute, you're going to want to change that into radians per second. So we actually have two steps here, right? We're going to do 1 rev is 2 pi radians, and we're going to do 1 minute is 60 seconds. And so if you multiply all the way across the top, multiply all the way across the bottom, let's see what we're going to get. We're going to get, it looks like a nice clean 6 pi radians per second. So this is going to go in here as 6 pi radians per second. That whole thing gets squared. It gets multiplied by the radius, which is in meters. Then you notice the meters are going to go ah and scare the radians away. And so if you multiply that together, just be careful with your calculator when you do 6 pi. Make sure that whole quantity gets squared, and you multiply by 0.12, and that's going to get us 42.6. So our AC here is 42.6, and that's going to be in meters per second squared, our radial acceleration. So there's your two answers for part C. All right, so the next one's going to be a little shorter, which is nice, but just to do a quick recap here, all right, we saw one of our kinematic equations here. We saw another one of our rotational kinematic equations here. And then the part C, the real trick to that was just knowing what in the world they were talking about with radial acceleration. And if you keep in mind, radial acceleration sometimes used synonymously with tangential acceleration, with centripetal acceleration. See, there's so many accelerations to keep straight. Then you're good to go. Let's look at one more, the London Eye. We're going to take a trip over to the pond here. And it looks like that one has a radius of, let's see, 67.5 meters. Cool. At its cruising angular speed, it takes 30 minutes to make one complete revolution. Okay, so what does that mean? It means 1 rev per 30 minutes is our omega final. How do you know that, Mr. Simpkins? Well, rotational speed is in revs per second or radians per second, right? And so we see the one complete revolution. We just got to divide it by time. And then let's clean this up a little bit. Since it's not asking us later anything about revs or anything, why don't we put it in our standard units, which is radians per second. So I'm going to have to do two little conversions here. 1 minute is 60 seconds. 1 rev is 2 pi radians. Multiply across the top, multiply across the bottom, and it looks like our omega final is super tiny. It is 0.0035 radians per second. So just multiply across the top and bottom there, that's what you're going to get. Let's keep trucking. It says it takes 20 seconds to bring the wheel to that speed. So t equals 20 seconds to get there. And, sorry about that. And it says it's constant. Sorry, what's the angular acceleration during startup? So angular acceleration is going to be our delta omega over t, which is going to be omega final minus omega initial. If it keeps doing that, stop. Okay, so over t, which is that guy. And so we're going to plug this in here. We're going to have 0.0035 radians per second divided by 20 seconds. If you thought that number was small, wait till you see this one. 0.0035 divided by 20. Boy, that's tiny. All right, so this guy, angular acceleration, is 0.0000175 radians per second squared. So that's super tiny. That's the acceleration, angular acceleration to be specific, during startup. All right, what's the angular displacement of the wheel during startup? The angular displacement, as a reminder here, that is asking you angular displacement is for delta theta. So we can kind of truncate our longer kinematic equation. And the reason we can do that is because the omega initial term is 0. So if you're wondering where does that come from, that comes from this equation on your equation sheet. No, alpha. Comes from that equation, but omega initial 0 and theta initial is 0. So that's how I got to that shortened version of that equation. And that's just going to be 1/2 a, so 0.000175 radians per second squared, times our time, which is 20 seconds. And that, oops, sorry about that. And that one gets squared, like so. And so I'm going to multiply our answer by 20 squared, which is a pretty large number. And so this one, the delta theta, is going to be 0.07 radians for our angular displacement of the London eye over those 20 seconds. All right, so those are two quick little problems. What I want you to notice here are that our rotational kinematic equations look the same as far as the format and the layout goes for our translational kinematic equations, the ones we started with this year. It's just you got to get real comfortable with the terminology and the different variables that are at play. So till next time, I'm Mr. Simpkins in the Simpkins Physics Corner.